In our previous video, we talked about orbital diagrams, and so in this video, we're gonna talk about orbital diagrams. We're gonna expand upon it all the way up to krypton, atomic number 36. And what we're gonna do is we're gonna convert orbital diagrams into electron configurations, and you'll find out that they're much easier to write, and they don't involve so many boxes and arrows. So let's get right to it. So previously, we'd already talked about how we can use the periodic table to guide us through orbital diagrams and electron configurations. And what we said was, if you were in period 1 and you had this block right here, this block that is 2 elements wide, these guys were our S block. And then we went over here to our the other side of our period table where a lot of the nonmetals are. We said this block was 6 elements wide, so that's obviously going to be our P block, correspond to 6 electrons. And then down here in the middle, we have our transition metals, which is 10 block wide, which corresponds to our D block. And then down here at the bottom, we're going to have our intertransition metals, which is going to correspond to our F block. Okay, and we said we could use these to predict what would come next in orbital filling and on an orbital diagram and electron configuration. For example, we're going to start here in period 1, and because we have our S block, this is going to be our 1s. So let's say we were going to do, just as a review here real quick, we were going to do orbital diagram for sodium, which has atomic number of 11. So of course we're going to start right up top with hydrogen, and there's our 1s block. So we draw a box with this 1s. Goes straight across. That takes care of hydrogen and helium. Comes down here to period 2. Now we're still in the S block, so now we still have we're in our 2s. We go straight across, still in period 2. So now we're going to enter our P block, 2p. We wrap back around here to period 3, and there's our sodium, and so there's going to be our 3s. Okay, so now let's go ahead and fill these guys in. And so putting arrows equaling the number of electrons that a neutral sodium atom has. So remember the rules. We start with our lowest orbital, lowest energy orbital, which is our 1s. We go ahead and fill that up with opposite arrows, opposite spins. Then we go onto our 2s, fill that up. We get to our 2p. We have to remember that we want to have 1 electron in each of the equal energy orbitals. So there's 1, 2, and 3, but we still have more electrons to go, so we're going to go ahead and go back and double them up. 4, 5, and 6. So right now, let's go ahead and count our electrons. We have 2, 4, 6, 8, 10, and so we want to get to 11, so we have 1 more electron, and there we go. There's our 11th electron. And so that would be the orbital diagram for, I'm just going to erase a couple things here. That'd be our orbital diagram for sodium. But let's say that we wanted to do something a little bit crazy, and we wanted to maybe go all the way up to xenon, which was atomic number 54. Drawing these boxes and arrows gets a little tiring. So we can do a couple things here to help ourselves out and make this go quicker. And so what we're going to do is we already have these orbitals all broken up into 1s, into 2s, 2p, and 3s. And so what we're going to do is what's called an electron configuration. And in electron configuration, what we're going to do is take our labels, for example, the 1s, and then we count the number of electrons that we have within the 1s box. Right there, there's 2, and so we're going to write that this way. And the way we read this is 1s2. That's our first part of our electron configuration. Then we go to the next one. We go 2, because it's going to be our 2s, and there's also 2 electrons in there, and so we write 2s2. And then we go to our 2p. And in the 2p, we have 2, 4, 6. So we're going to say 2p6. And then we go on to our 3s, and there's only 1 electron in there, 3s1. This is an electron configuration. Much easier to do. It still tells us a lot of information about the atom. Still tells us that a sodium atom does have 1 electron in its outside orbital, that s orbital, which is spherical, and it's in 3s. Okay. Now, what I'd also like to do is talk about how we can continue on the periodic table up into some higher energy levels. So let's get scrooched down and we'll do that. So again, just quickly labeling these. There's our S block there. Obviously, these guys are going to be our P block. And we've got our D blocks 10 wide here. And then we have our F blocks here. Okay, so then again, if we're starting at hydrogen, there's our 1s1. Going over to helium, there's our 2, or excuse me, oops, that's still 1s there. There's 1s2. And then we get down here and we get to 2s, and then lithium and beryllium, 2s1, 2s2. Straight across we have 2p. Come back down to sodium, 3s. Straight across we have 3p. And then we come down here to potassium and calcium, and we get to our 4s. Now something very interesting happens right here. What we get is a drop. You would think it would be 4D, but it doesn't. It isn't 4D. What happens is we get a drop down and we get a 3D. And so going across this first period of our transition metals, scandium here would be 3D1, then 3D2, 3D3, 4, 5, 6, 7, 8, 9, 10, all the way to zinc. Zinc is right there at the end, right there. And that's going to be our 3D10, and then it resumes back to the pattern. Because we've already used 2p and 3p, now we're on to 4p right here. So gallium would be 4p1, up to krypton 4p6. Come back down here again, and we get our 5s block. Again, we drop down 1, and so we have our 4d block right here. And then we go to our 5p and so on and so forth, okay? So if you can go up to krypton, right now you're probably doing okay. So let me show you how this all works out real quickly here. Let's say we're going to have you do an electron configuration for titanium. Titanium, really strong light metal, used for a lot of things like fighter jets and bicycle frames, parts sometimes too. Sometimes when they do a hip replacement on a person, they might use a titanium hip. So we're going to start up there right at the top with our 1s, and so we're going to go 1s2. By the way, titanium has 22 electrons in a neutral state. Drop back down over here to our 2s, 2s2, straight across to our 2p. There's our 2p right there, and we have 2p6. Back down to our 3s, 3s2, straight across to our 3p6. Coming back down over here to our 4s. And I'm going to kind of drop it down here and go 4s2, and then come across and we have our 3d and 1 3d2, so it's going to be 3d2. And so that's how we would do, that's how we would enter. What happens is the s orbitals are slightly lower energy, the 4s orbitals, than the d orbitals. They fill first, and then we go back and start filling in those 3d orbitals as well. Okay, and so that'd get us all the way up to at least argon. We could easily do up to xenon as well. Much easier way to write electron configurations. And in the next video, we'll talk about how we can make this one even shorter by doing noble gas electron configuration. We'll talk about that in the next video.